Today, let's talk about proof of balance. So this topic is actually pretty complex. If you're not aware of the proposal that's been going on, I suggest that you take a look at it. It covers some of the topics that are covered over there, but not going to be discussed here. But essentially, what you want to do in this proof of balance is that you want to show nullifiers and you want to show a zero knowledge proofs that establishes that these nullifiers are correct. They are not spent or already. They are the response to nodes that exist. Then you make a signature over them, and you also have a value commitment that allows the system to figure out the total amount that you provide. So it's pretty much the same mechanism that is used to make a regular transaction, except that in this case, there are no outputs. You're not spending coins really, and the signature hash will be done on a different set of values, so that the resulting signature can be verified in the context of a proof of balance, but not usable to spend these coins on the main chain. So all in all, that's the way it works. The, the one drawback that this proposal has is it reveals the nullifiers. The nullifiers that you show are the ones that you would use if you were to spend these coins. And if you have spent the coins, they are the nullifiers that you have shown. It's possible to do like a retroactive proof of balance, essentially showing that at a point in the past, you have owned a certain amount, but not anymore. So all you have to do there is to set a snapshot height, and if the nullifier that you are putting in the proof of balance has not been used at that particular snapshot height, it means that you are still in control. If afterwards it appears, then you have spent it at a later point, but it doesn't really matter for that particular proof of balance. But all in all, the main point here is that there's only one domain, of, if you want, where these nullifiers are coming from. Right? The nullifier, just a small recap, the nullifier is essentially an ID hash of your node, but the hash of your node when you spend it. You have a node, you hash it to make the output hash. So what you have at the output of the transaction is it's called a node commitment. It's basically a hash of the real node. But when you spend it, you don't show the node commitment because that would link the input to the previous output. You are showing a nullifier, and this nullifier is essentially a hash of the commitment. So then the nodes are related in because the nullifier is computed from the node commitment, so they are related. But it's not possible to see how that they're related unless you have the you know the algorithm and you know the key that was used to calculate that hash. So that's all well and good, but because the nullifier is unique for a particular output, then if you are making several proof of balances, if you are making several proof of balances because you are using them to make elections, carry out elections, then these nullifiers will be a very easy way to link these ballots. The ballots will have the same nullifiers across different elections, and then anybody can link the decision, the value of that vote between elections. Obviously, inside a certain election, you cannot reuse the same nullifier because this would be like double voting on a particular election. But across election, it would be possible. So the proposal here that I want to discuss, and it's coming from the guys at the ECC, the engineers at the ECC, is how to make the nullifier election specific. So if you have, for example, election for the committee, the decision to renew or cancel or change the dev fund, you could have a vote that uses a particular election ID, and if you want to just show that you have a certain balance, you can have another vote that or another proof of balance that uses another election ID or of domain ID. We could just call it domain ID. And if the domain ID is different, and we can make it different by just hashing some standard value, then it would not be possible to correlate, to link these nullifiers, even if the same node is used in different elections. Okay, so that's the crux of the idea, right? You add in a calculation of the hash for the nullifier. Nullifier is a hash, so in a formula that involves this nullifier. Let me switch to actually the let me switch to the paper. This is a paper, and now we have the nullifier formula. So this is the formula, derive alternate nullifier, but this one is the one that has the domain. And the domain here is arbitrary value as long as it has a different one between each election. If the normal nullifier doesn't have this term, and it's just here the PRF of NK, and NK is your nullifier key, something that only you know. And this term, everything is pretty much the same except that we don't have the domain. So this will ensure that the nullifier that you are going to publish as part of your proof of balance is not going to be the same as any other nullifier, including the one from the main chain. But by doing so, there's a major problem that we have now, is that we can't easily figure out whether the nullifier, the node that you are showing, has been used on the main chain or not. So we don't know anything. We can ensure in zero knowledge that nullifier is calculated properly from the node commitment. The node commitments don't change, so we can check if we have to update the ZK circuit, of course, because the zero knowledge, the orchard circuit does not contain that domain parameter. So the nullifier that's calculated there is not going to match the nullifier that we're going to publish in the proof of balance. But if you update that, it's not super complicated to do. You're gonna have a new domain nullifier that will match the one that you publish in the proof of balance. But the other problem that you have now is that this domain nullifier is completely different than the ones that you have on the main chain. So it's possible that you are showing a node commitment. You're showing a nullifier for a node commitment that is already spent. Right? If you remember, the way we know that a node is spent, is not double spent, is because the nullifiers are public. And if you are trying to spend the same node again, you would have to broadcast the same nullifier twice. And a node, a verifier, a full node, will check that the nullifier is only used once across all the transactions. So that would fail and it would not be added to the blockchain. But now you cannot do that anymore because the nullifier in the proof of balance is going to be different than the nullifier on the main chain, even though the node is the same. So you don't have that technique anymore. So you need to have something else that allows you to show that the nullifier, the node that you have, is not already spent. And that's a technique that is pretty it's not super new, but it's something that has to be added to our proof of balance. So we have already a technique that allows us to, it's pretty standard, to show whether something is part of a set. If the set is public, if we know all the elements of the set, and you want to show that you have a certain parameter that is part of that set, without showing that value, then you can do that with what we call a Merkle proof. So the idea of a Merkle proof is that you put all these elements, these values of the set into a tree. You hash all the tree, and then you have a common root. You have a root value that essentially captures the entire set of values. If somebody changes any value, the root will be different. If you add something to the set, the root will be different. So that tree and the root of the tree captures precisely the set of values that are in there. Now, if you want to say that you are using a value that is part of the set, you can export, you can build something called a Merkle proof. The technique to do that is not very important, but all that matters is that you will provide information that shows that element you have is part of the set. And this proof, you can do it normally. You can do it in a normal algorithm. But if you do that, you will have to provide the proof. I'm not going to be a zero knowledge proof. I'm talking just about a proof of inclusion, that your element is part of the set. So you have to provide that proof of inclusion along with the data. But you can also do that in a ZKP circuit. So if you do that in a ZKP circuit, it's interesting, more interesting, because you can keep the proof of inclusion and the data that you want to say is included in the set. You can keep these two things private. All you have is then the root of the tree, which is public knowledge, and the proof that what you have done is actually really following the steps of creating that proof. So it's kind of interesting because in a sense you have a proof in a proof, right? The zero knowledge proof is proving that the proof of inclusion is calculated properly, right? And it's kind of cool if you think about it this way, but that's not super. I mean, it's something that we wanted to do with CKPs because that's the idea that you can run algorithms, calculations in a normal way, like step by step, and you can do the same thing in zero knowledge in a circuit, in a Halo 2 circuit, and that opens the door for like making proof of proof, right? The recursion thing. But just let's go back to the topic at hand. Now we want to use the same technique to show that the nullifier, the real one, not the nullifier from the quant proof of balance, but the real nullifier, so the nullifier that is part of the main chain, is not used. Right? And we cannot do that by publishing it, right? Because if you publish it, it's game over. It's back to the start. Everybody will know that that this is a nullifier that you're using, and we're back to have linkability between the votes. So now we want to show that the real nullifier is part of the is not part of the set of published nullifiers, but you want to do that without showing the nullifier. So this is the opposite of what we usually do. We usually want to show that we are part of the set. Now we want to show that we are not part of the set, right? So the not part of the set is the fact that we're talking about exclusion tree, right? So we have the nullifiers, but we want to show that our nullifier is not one of them, right? Because all of these are already used, or already spent. We want to show that we are not spending something that has been spent before, right? And the one of the technique is to essentially extend the set to include every possible node out there, nullifier out there. So it's kind of brute force, but the idea here is that to prove that you are not in a set, right? You make a set that has all the elements that are missing, right? So, for example, if you have a set of the numbers 1 to 10, and you want to show that you are not 5 or 6, then you make a complement set, which has 1, 2, 3, 4, not 5, not 6, 7, 8, 9, 10. You make that set, and now you show that your value is part of the complement set, right? So you are turning the problem of exclusion into inclusion in the opposite set, which theoretically works with no problem doing that. Then you can use your previous technique where you use the proof of inclusion that we discussed earlier. That it works. The only problem with this technique is that by creating the exclusion set, now you have a set that is extremely large. Right? We have not a set nullifiers. We would have maybe a few million, maybe a few tens of millions, or eventually hundreds of millions. But the exclusion will be any possible value that the nullifier can get. So that is like in the millions of millions of millions of millions of millions of millions, right? To power 256. So clearly, if you go brute force, if you try to make in memory create the complement set, it's not going to possible. You don't have enough time in the universe, enough memory to do that. The brute force technique is clearly not going to work because there are more non-nullifiers than there are probably atoms on Earth. So the number is extremely large. But we can figure out that this is actually mostly empty. We can optimize this data structure by saying that 99.99% of the nodes are empty. So we can calculate the same proof of inclusion in a more optimal way that doesn't require us to actually build the entire tree element by element. So there's optimization, and clearly we can do that. The result is actually not bad. We could do that. The only issue here, though, is that the proof that you are going to show, the proof of inclusion, remains pretty long because now the tree that you have is going to have 256 levels. Right? The tree that contains all the possible nullifiers has to be very large because it has to contain everything. And essentially, you would have 256 levels because it has 2 power 256 leaves. So it's still doable. You still can do that. But what is suggested in the what we implemented is more subtle than that. So instead of making a brute force tree that has everything, the opposite of everything, the complement set, we are going to capture this complement set by putting ranges, right? So instead of saying that you don't have, an example, you don't have 1, you don't have 2, you don't have 3, you don't have 4, and you have 7, 8, 9, 10. We're going to say that you have a range 1 to 4, and then a range from 7 to 10. Right? So this captures the same information, but in a much more compact way, because now you can see that essentially you have the same number of intervals that you have dots. Right? If you have these nullifiers and you replace the complement set by ranges, then the ranges are about the same number as the nullifiers. Because we're talking about, if you are talking about posts, right, and then intervals between these posts, you have the number of intervals is the number of posts plus 1, because you have 0 and you have infinity. Well, you have 0 and you have max. Right? All in all, it's really much more manageable because we are back to a tree that has about the same size as the nullifier tree. And if you use these ranges, right? So you can build the same tree as before, but instead of having leaves that are just values, the leaves will be these intervals. Will be in our case 1 to 5, 1 to 4, and then 7 to 10. So you have these two intervals, and these two intervals are going to be the leaves. And everybody can calculate that, right? This is not private information. You can calculate that tree based on all the nullifiers that have been out there. Right? So calculating that tree, this is reference data. Everybody can do that, right? Everybody will come up with the same root of that tree at the end. But now, if I want to show that my value is inside the tree, uh, what I do is, instead of giving my nullifier and have a proof of inclusion, I will give the interval where this nullifier belongs. So, for example, if I want to prove that 3 is part of that, 3 is not used, I would figure out from my side, because I know the value is 3, I can figure out that it's part of interval 1 to 4. And then I will provide in zero knowledge that the interval 1, 4 is one of the intervals of that have no nullifiers, right? So I don't show the 1, 4. So as before, when I was doing inclusion proofs, I don't have to show 1, 4 and the proof. I can do that in zero knowledge. Right? So I just say that there is a range that I'm going to be using. And that range is 1, 4, and that range is part of the set. But I'm not actually showing 1, 4, right? I'm using 1, 4 in my circuit as a secret, and still have to prove that 1, 4 is part of the possible sets. And now that I have locked down this 1, 4, I must also say that my nullifier, the one that I don't want to show, my really my nullifier from the main chain, the Zcash chain 3, is belongs to that set. Belongs to that interval. So 3 has to be lower than 4, and it has to be greater than 1. Right. So now I have switched the proof of exclusion into a proof of inclusion plus a proof of range, that my nullifier is part of that range. So I have to prove two things. I have to prove that I know some secret information, which is that range. That range belongs to the range without nullifiers, and that my nullifier belongs to that range. So a bit more it's more complicated, right? Because now we have more than just a proof of inclusion. We have two proofs of inclusion. We have a proof of inclusion of the domain nullifier. We have a proof of inclusion of the nullifier exclusion range. And when we have a proof of a range proof that our nullifier is part of that range. Right? So we have three things. Okay, that's it. That's the main thing. Okay, so for a demo, right? How do we do that in practice? Let's switch to some code. And the code is basically this code, right? All right, so this is a sample code where we test this workflow. So first we have to pick a domain nullifier. Here I randomly pick domain nullifier, and since it's a field point, it's like a secret key. There's nearly no chance that this is going to be used by somebody else. Then I'm going to say that I'm going to spend that node. right? So I'm creating a dummy node for the test. Therefore, it's just a random node, right? Using a random number generator to create that node. So at the end, I will have the spending key for that node, and I have the full viewing key. But that node has no value. All the dummy nodes have no value. So therefore, what I do afterwards is I use the address that the node, the random node has created, but I set the real value, and I set the value to be 1 million Zats. So now, after on line 28, I have the real node that I want to prove I own, and I have the full viewing key, and I actually even have the spend authorization key. So I have basically the secret key, the public key, and I have the address. All this because it was randomly generated, right? So in order to make that transaction, I would go through the normal process, which means that that node, I also have to calculate its commitments, its hash, normal hash. That's here. We calculate the node commitment. And that node commitment is then used to calculate the nullifier. So the nullifier is then calculated from, actually it's calculated from the node commitment, but the API allows you to calculate the nullifier directly. So we calculated this nullifier directly, and that would be the nullifier from the main chain, the normal nullifier. But we also wanted to calculate our new nullifier, or our domain nullifier, that is specific to this particular proof of balance. So we have now two nullifiers. We have it's called NF old because it's the nullifier for spending. Then we are going to make our transaction. So to make that transaction, we have to pretend that that node is coming from a previous transaction. So I'm making a tree of node commitments. Normally, you would build that by scanning the blockchain and recording every transaction output. Right? So I'm creating like 100 random node commitments, and I put my own node in the middle of these. Right? So there are 60 random node, then the node that we just created, and then another 60 random nodes. So now we have basically our test commitment tree, our test output data, node outputs, and we can calculate the root of that, right? So that normally when you do that, you get the anchor, and the anchor is the stuff that you can look in the blockchain, the Explorer. There's a block anchor, and that's simply the root of the tree that we were building here. But now we have this new stuff, which is the stuff we're talking about, where we are building the intervals where you have no nullifiers, so the exclusion intervals, and you want to calculate the root of that tree. So first of all, we want to calculate that tree. To calculate that tree, we collect all the nullifiers we have, we sort them in ascending order, and then we're making these intervals where it starts at 0 to the first node, and then from the first node to the second node, to 0 to the first nullifier, from the first nullifier to the second nullifier, so on and so forth, right? So that's the logic here, right? We basically go from 0 to n. N is the number of nullifiers we randomly generate. So all these nullifiers are not the one that we have, right? These are the nullifiers corresponding to stuff that we are already spent. We don't want our node to be one of these because then it would be a double spend. But since all these guys are picked randomly and the space is super large, it's very unlikely that randomly we are picking the same value twice. So all these nullifiers are most likely going to be all different. And then we have these intervals, and we build the same logic as before. We use the same data structure where we put these guys into a tree, And at the end, we calculate the root of that tree. So that's the root that also currently is not part of the blockchain because this logic is not there, of course. But this is data that is public, and essentially anybody can calculate that. And if it's a election process, this value will be checked by the software that is verifying the votes. So that value has the root of the exclusion tree is something that we can agree on. Part of this scanning of this building, I'm also checking for where my nullifier belongs, in which of these intervals this nullifier lays. And this is going to be NF start and NF end, right? So one of these intervals and only one of these intervals, because all these intervals are not overlapping, are disjoint, and they cover everything except for the nullifiers that are used. So since my nullifier is not used, it should belong to one of these intervals and only one. And now that I have that, I have this interval, I have all the data I need to produce my zero knowledge proof, right? And again, most of this was public, except for my own nullifier that I want to keep secret, and also the interval where that nullifier belongs to. That is also some private information, that's secret information that I don't want to reveal. I don't want to reveal, even if it was a range, I still don't want to reveal what range my nullifier is. That's would not be very big information, but that's already information that that we want to avoid using revealing. So that all this stuff, nullifier and nullifier range, is going to be secret input into this proof of balance circuit. So this proof of balance circuit is a different circuit than Orchard. So it's mostly the same, except that it has these additional constraints. So then I run the zero knowledge circuit, and that gives me a proof. And again, that proof has to match some of the public data. The public data being the root of the exclusion tree, that is public information that has to match, and also has to match the domain nullifier that I'm going to produce. So the difference is that I no longer produce my nullifier, right? The public data excludes the nullifier from the Zcash chain that I don't want to show, and that's the main part of this work. I don't want to show that, but I'm going to show the addiction domain. Right? This zero knowledge proof is tied to this particular addiction domain. It's tied to the root of our nullifier exclusion tree, and obviously it's tied to the domain nullifier that I'm going to provide. Right? By providing this domain nullifier, I allow the election software to prevent double voting. The system will check that the domain nullifier is not part of two vote submissions, and therefore I'm not trying to double count my coins. And then if I run it, I should have everything goes well. I will have a proof that I can then verify. I can create a zero knowledge proof here, and I verify it. First, I run the debugging prover, and afterwards I do the same, but in a more realistic environment where I first create the proving key and the proof. So we have a proving key and we have a proof. And then a second environment where we are only verifying. So we have now use the verification key, verifying key, and we are in the context where we don't have the circuit anymore. We don't have the secret data, but we have the proof, and we have the public data, and this should verify to be correct. right? So this is the workflow of the example, which basically carries through the entire logic of providing a proof of balance, a shielded proof of balance. All right, so let's go that. Let's do that. We have target, release, and test proof of balance. If we run this, so the first stuff is pretty fast because there are very few nodes. Now we are creating the proof and verifying the proof, and it's all done. So, so the entire process went through. All right. That's the ZKP. So that's the circuit. That's a demo of the circuit that has been adapted to work around the limitation of exposing nullifiers. So that's as described in the draft zip by the ECC guys.